Okay, so today I want to start chapter 7, analysis of variance and the classical Wallis test. This is non-parametric version of Hanover. Okay, and chapter 7 slides are available on the website. And the next Tuesday, I will discuss the final projects. So at first, I will ask you to submit a final project plan so that I will discuss how to create the final project plan. Do you have any questions on quizzes or any the lecture material? I haven't seen your midterm yet. Okay, so I think I have to share the screen. And so chapter 7, analysis of variance. So analysis of variance is a kind of generalized version of t-test. So in t-test, we compare two groups. For example, the control group and the treatment group, or maybe the apples to oranges, maybe size of apples and size of oranges, and see if the two groups have difference. And analysis of variance, we extend it into several groups. It's possible that the entire population is divided into 3 or 4 categories, maybe even more. For example, that if we compare the stock return of companies in different industries, the infotech or the energy industry or banking, that we have multiple categories. So we want to see if the category affects the stock market return or not, or simply maybe 3 different animals. Then we want to see if these animals have entire, overall different lengths or not. So that kind of things we have to test. So analysis of variance is a kind of the testing method. And several references, the R book and the Faraway's lecture note, and also Faraway's book. Yeah, but still the slides are self-contained, so you don't really have to refer book if you don't feel it's necessary. And at first, we have the one-way analysis of variance. So one way means that we have one factor. So maybe the group have different factors. For example, if we have the 100 observations of the people, then they have multiple factors such as maybe gender or maybe race or blood type and so on. So we have only the one variable, one factor. Then we say that analysis of the group is called the one-way analysis of variance. So variance, yeah, so generally to test something that we use the variability, so that we say analysis of variance, but the variance, yeah, it sounds a little strange, but we say this as analysis of variance. And the assumption is like this. So we have the group A, group B, and group C, and it have some observations. Different groups may have different number of observations. From group A, we have n sub 1 observations, and from group B, n sub 2 observations, and from group C, that we have n sub 3 observations. So maybe 3 observations from here, 5 from here, and 7 from here, something like that. And we assume the same assumption as the t-test, so equal variance t-test. So basically we assume that x1i that follows the normal distribution with some mean, just some mean, the mu1 or something, but we have the same variance. So x2i follows normal with this different mean, but the same variance. And x3i follows the normal with the same variance. Maybe the mean is different, but we assume same variance. So if we have two groups, that is exactly the assumption for two sample equal variance t-test. But if we have more than two groups, we have to generalize it. And sometimes people ask why we can assume that these variances are the same, even though we don't really know, if we don't even know the means are the same. So it sounds a little strange assumption, but basic idea is that usually we want to see difference in mean, and the variance is not most important quantity. So just for convenience, that we assume those are the same. Yeah, so yeah, sometimes it's reasonable to assume sigma squares are the same. For example, that we consider 3 different factories and making the products of different weight, but those machines used to make the products have the same precision or something. So the variability in size of the product is the same, even if the size of the product is different. Okay, so one-way layout, the assumption is this. So we have the observations x sub ij, and x sub ij is determined by the group mostly, but we have some error term, epsilon ij. And epsilon ij is normal 0 sigma square IID. So the follows normal distribution with certain variance and the independent each other. And the error size is the same for all observations. So you can see, for example, that we have the 3 groups of animals, then each animal have average weight, the population average weight, but we have also the variation in weight between individuals. So we have error term epsilon ij. So xij represents the jth observation of the ith group. And as seen in the previous slide, the ith group has the n sub I observations and mean alpha sub I. Sorry, in the previous page I wrote mu, but I'm using alpha. And what's our objective? Our objective is testing. So we are extending the t-test. So our objective is that all means are the same. And the alternative hypothesis is the sum of ij's, alpha i's are different. So alpha I is not equal to alpha j for some pairs ij. So this looks a little vague, but basically we want to see if this factor has some information or no information. So in real world example for 3 groups, usually we want to see if alpha 1 is different from alpha 2, or alpha 1 is different from alpha 3, alpha 2 is different from alpha 3. So we want to ask these questions, but here it's the null hypothesis is a little different. So everything are the same, and against some pairs are different. Yeah, and the alpha i's are parameters. So this is population mean of each group, and epsilon ij's are random variables. So xij is alpha I plus epsilon ij. Constant plus random is random. So the xij's are random variables. And some notations, the xi bar, this is the group mean. So ith group mean. And x bar dot is overall mean. So it is convenient notation, intuitive notation. So x bar I, that is the mean of ith group, and x bar dot, that is the mean of all observations. And here, yeah, so naturally the xi bar is defined by just the sample mean of the observations within ith group. And x bar dot, this is the average of all observations. So we add up all sample size, all the sample size for the group, then let the summation as capital N, then x bar dot is 1/n times summation of all observations. I got the question. Can there be a different number of observations for different factors? Yeah, so different groups that we have different number of observations. So N1, N2, N3 may be different. Yep. And usually we say just a factor. So factor include the multiple levels, multiple groups. And we want to define several complicated quantities next. So our objective is to evaluate whether all alphas are the same or some alphas are different. So basically, we consider the variability within the group and the variability between the group, and we compare the ratio. So that is the idea. So within each group, we have some variability in observations, right? So we have 10 observations in group 1. So those 10 observations have variability. But also, if we calculate the group mean for group 1, 2, and 3, those have some variation, right? And we compare those variation to test if alpha i's are really the same or different. Intuitively, so think about the box plot. So group 1, group 2, and group 3. Sorry. And the group 1, okay, so this is some measure, for example, the height of the animals of these 3 groups. Then group 1 has like this, and group 2 has height like this, and group 3 have height like this. Then you can see these groups have different means, but within group, the variation is very small. In this case, we can conclude that the alpha I, alpha 1, alpha 2, alpha 3 are different. Right? And even if the group means are the same, if the variability is much larger, probably we cannot get the same conclusion. If the 4 observation in group 1 is like 1, 2, 3, 4, and the group 2 is like the 1, 2, 3, 4 or something, then it's more it's unclear whether the group 2 is really larger than group 1. The height of group 2 is larger than height of group 1. So really, we have to compare the 2 variability. So one is variability within each group, and the other is variability between these group means. So we want to quantify those 2 measures. So first, SSDW, that is the sum of squared deviation. So sum of squared deviation within group. So W stands for within. So you can see the within group, we calculate the deviation, Xij minus group mean. So how much Xij deviates from the group mean, and take a square and take summation for all j and all I. So that is basically, we compare this with this, this with this, this with this, this with this, and this observation with this mean, this observation with this mean, and so on. So this is the SSDW, sum of squared deviation within groups. And the next one is SSDB. B stands for between. So basically, we take the difference between the xi bar and the x bar dot. So x bar dot is overall mean. So basically, we compare these 3 means. Actually, the overall mean is probably around here. So we compare the overall mean, this is x bar dot, with these group means. But of course, we only have 3 group means. So we want to add up these numbers for the number of observations. So for each the observation that we basically calculate, for each observation we calculate the group mean and the overall mean. So still we take the summation of the same number of terms. So that is SSDB. But of course, the group mean is the same for the all observation within a group. So this part, this summation, so this summation, so NI observations, anyway, XI bar is the same. So we can write this as NI times this. So this is SSDB. And the another quantity, SSD total, TOT stands for total. This is total variation. So we compare each observation with the entire sample mean. So Xij minus X bar dot. Then we take summation for all observations. So this is named SSD total. And if we manipulate some algebra that we use the property of Xi bar and X bar dot, that we can prove that the SSD total is summation of SSDW and SSDB. So intuitively, this is within. So this is named as sum of scalar deviation within group, and this is between groups, and this is total. So it's somewhat reasonable that this plus this becomes this, but certainly we need a proof. But the idea is, okay, so we compare SSD and SSB, sorry, SSDW and SSDB. And if we take the ratio, at first we have to standardize this SS between by this I minus 1. So it's a little bit hard to see, but this is I. And the SSDW. So SSDW divided by N minus I. So this is I again. I is the number of groups. So after this, kind of standardization, that we can show that this quantity SSDB over I minus 1 over SSDW over N minus I. So this is equal, this follows the distribution, the F distribution with degrees of freedom I minus 1 and N minus I. And this numerator is called mean squared between groups, and the denominator is the mean squared within groups. So these two terms are defined by this numerator and this denominator. So actually this distribution, so this quantity follows this F distribution under the null hypothesis. So I think I have to say that this is under null hypothesis. Null hypothesis is alpha 1, alpha 2. These are all the same. So based on this, we can use this as test statistic to see if this null hypothesis is true. Any questions so far? Yeah, I appreciate some students ask many questions during class. Yeah, and these are just names I have discussed. And so F statistic. Okay, so the how to test is the next objective, and this F is the ratio of basically SSDB over SSDW. If F is large, that is the SSDB. So deviation between is relatively larger. So, or maybe mean one. So MSB is relatively larger. That means the variability between groups is larger. So this implies that the H naught is unlikely. H naught is the assumption that the all groups have the same mean, but the group means are different each other. So this is unlikely. So reject H naught. So basically the procedure is that if F is larger than some threshold, then we reject H naught. So that is the threshold. That is the criterion. And if our significance level is alpha, so this alpha is significance level. So if we have under null hypothesis, this F statistic is within this extreme high range, that is F sub 1 minus alpha. If our test statistic falls in this range, they reject H naught. So this is rejection region. So this is the how to test null hypothesis. Yeah, so this is the basic idea of the ANOVA. And the next topic is actually we want to see the ANOVA is very similar to linear regression in some way. So in linear regression also we can, for example, estimate, we can test if some coefficient of some variable is 0 or not. So in linear regression, so if the y is equal to beta naught plus beta 1x plus epsilon, then we can test if the beta naught is equal to beta 1 is equal to 0. And this is similar to ANOVA situation. So here x is a continuous variable. For example, we want to see height is affected by weight or something like that. So we want to see the effect of x on y. But conceptually, it's similar to ANOVA. In ANOVA, factor has only, finite levels, but here x is continuous variable. But anyway, we want to see if some, predictor affects the y. So it's a kind of similar. And when we consider matrix representation, we can see that those are almost the same. And here is a very small example. We have the 7 observation in the data set, and we have 3 groups. So first 3 observations are in group 1, and the following 2 observations are in group 2, and the last 2 observations in group 3. And these are numbers. So these are xij. So to be exact, x11 is this, and x12 is this, and x13 is this, and x21 is this, x22 is this, and 31, 32. So this is the situation. So n1 is 3, n2 is 2, n3 is 2. And in ANOVA model, actually, if we use a matrix representation, the situation can be written as this. So you can see that these 3 observations, first 3 observations are in group 1. So that should be, for example, the 10.1 should be equal to alpha 1 plus epsilon 1. And if we use these matrices, then we can express this as one equation. So this is pretty similar to the simple linear regression. So if we write this as y, this as x, this as beta, and this is epsilon, exactly y is x beta plus epsilon. So only the difference is this matrix was, just the n by 2 matrix in simple linear regression. But here, actually, the n by 3. If we have 4 groups, n by 4. And also, in simple linear regression, the first column is always vector of 1s because that express intercept. But here, it's slightly different. So just each column represents the indicator function of group 1, 2, and 3. But still, you can see this is very similar to simple linear regression. And actually, in chapter 11, that we will study the multiple linear regression, which have multiple predictors to explain why. And actually, that is a just generalized version of this ANOVA. So generally, the matrix X is a large matrix. In multiple linear regression, X has the multiple columns, the more than 2 columns. So exactly that's ANOVA is a special case of multiple linear regression. Yeah, I think that it will be discussed in 11. Actually, 12, it also discusses something about multiple linear regression. Yeah, and yeah, so because of this expression, sometimes people want to put this in a different way. So that is, we want to put just a vector of 1 as the first column, and the second column is just the indicator function of group 2, and the third column is indicator function for group 3. So this is a little more convenient because it's the same as the linear regression. In linear regression, the first vector represents an intercept, so the always 1. And so if we modify this as 1, 1, 1, 1, 1, 1, 1, so that is another expression of ANOVA. So that is the xij is equal to mu plus alpha I plus epsilon ij. Here, I is equal to 1 and 2. I would say alpha 1 is equal to 0. Yes, sorry. So I would say that xij is mu plus alpha I plus epsilon ij, and alpha 1 is equal to 0. Yeah, then actually we can express the same situation. So sorry, maybe it's a little complicated. So the previous model and this page, coefficient for group 1, group 2, and group 3. In the previous one, group 1 has the coefficient of alpha 1, alpha 2, alpha 3. Maybe coefficient, maybe it's a little vague. So the mean parameter for group 1, group 2, group 3. And previously that is alpha 1, alpha 2, alpha 3. But here, actually this is mu plus alpha 1, and this is mu plus alpha 2, and this is mu plus alpha 3. And we assume that alpha 1 is equal to 0, so this is 0. So this is the situation. So that means that in this page, the mu is the average level mean for group 1. And alpha 2 is the difference between group 2 and group 1. And alpha 3 is difference between group 3 and group 1. So that is the interpretation of these 3 parameters. So different people have different parameterization. Maybe I should rename this alpha 2 and alpha 3 since the meaning is different from the previous page. Yeah, and some people impose even different assumption, that is the summation of alpha i's are equal to 0 rather than alpha 1 is equal to 0. So in this case, the mu is the overall mean. And alpha I is the deviation of ice group mean from the center. Ice group mean from mu. So that is also reasonable. The mu is more easily interpreted I got one question. So you can add a prime to the alphas if you want to rename them. Yes, so yeah, we can put the tilde or yeah, prime or something like that. So it's slightly different. So maybe you can write the tilde or something. Okay. So if we use the matrix, we use the expression xij is equal to mu plus alpha I plus epsilon ij with alpha 1 is equal to 0. The expression is this. And this is usually the preferable expression in linear regression and ANOVA. So often we use this. And one note, matrix X of multiple linear regression. So multiple linear regression, the Y is explained by the multiple predictors. So that is beta naught plus beta 1 times x1 plus beta p times xp. x1 to xp are different features of observation. For example, we want to explain the weight of people based on the age and the gender and height and so on. So those are x1, x2, x3, and so on. So that is represented by using this, the predictor matrix X. So that's why we often prefer these pages, the expression of the model. And this X is sometimes called the design matrix. So it describes the design of the model, design of the parameters, maybe. Yeah. Any questions so far? Yeah. And this is one example and using iris data. So iris data, we have 150 observations, but we have 50 observations each for 3 different species, the Setosa, versicolor, and the virginica. So 3 groups. So if we make a box plot, actually the plot of this, the sepal length is a variable and the species is a factor, then plot of sepal length tilde, the species, makes box plots. And you can see the sepal lengths are most likely significantly different between groups. Certainly the Setosa, that we have much smaller values compared to versicolor and virginica. Versicolor and virginica have some overlap, but still, as a group, it looks significantly different. And how to run this ANOVA model, one-way layout. So that is actually done by the same function as linear model because of the reason I discussed. So linear model is very closely related to one-way layout. And the sepal length on species, then we can get this. So that means that this is mu plus, sorry, this is basically alpha 2 tilde, alpha 3 tilde. So mu expresses the overall mean. Maybe you can go back to the slide, and 5 is, sorry, the mu is for the mean for the first group. So that is Setosa. Basically, R uses alphabetical order, and Setosa comes first. So we can change it with using levels option in for an object vector. But okay, so in default, this is in alphabetical order. So we can see the overall level for the first group is 5, and the difference between, so this is the difference. So the mean of group 2, so mean of the versicolor minus mean of Setosa. And the next one is the mean of Virginica minus mean of Setosa. So Setosa is baseline. So this is the result. Okay, I got another question from another student. What is the difference between the matrix representations between the two parameterization? Again, yeah. So first parameterization, the matrix is here. So these are indicator variables, 1, 1, 1, 0, 0, 0. First column is for the first group, second column is the second group, and third column is for the third group. And here that we have all ones here. So it's kind of linearly transformed. So yeah, so that's the difference. So in this case, the first group actually, sorry about that. This may be, it may be better to put this as mu, right? So the first one, actually the first group, the mean is mu. And the second group, mean is mu plus alpha 2. And the third group, mean is mu plus alpha 3. Yeah, that's it. Yeah, and by this, the LM function, you can basically estimate the mean of the mean of Setosa first, that is 5.0060, and the difference between the mean of Versicolor and Setosa, and the difference between Virginica and Setosa. Yeah, actually it explains if difference is significant. You can see that okay, at first 5.00 is significantly different from 0. That doesn't have much information. So all flowers have sepal lengths more than 0. But the second one has non-trivial result. The Versicolor and the Setosa, we have actually the different mean. And actually this difference, 0.93, has standard error of 0.1. So certainly it's larger than 0. 0.93 plus minus 0.1, that is always positive. So you can see that this is probably significant. So we can say that statistically significant. And the difference between Virginica and the Setosa as well, it's significant. But our final objective is overall, these three groups have different means. And actually, this returns the p-value and f statistic. So f statistic is, remember, that calculated by MSB divided by MSW. And this is 119.3 on degrees of freedom 2 and 147. So roughly speaking, F distribution is around 1. So in F distribution, the expectation of numerator and the expectation of denominator are both 1. So basically around 1 over around 1. So that is around 1. So 119 is extremely large number. So the p-value is very small. So if extremely large f is observed, f distribution is like this. So extremely large f, more extreme probability is very small. So the p-value is very small. It's less than 10 to the power negative 15. Certainly less than 0.05. And yeah, so this is one way to test. And another way is to use the ANOVA function. So this is still the same, the linear model. But if we put the linear model in this ANOVA function, it returns this. And this exactly returns the MS between and MS within. So MS between and MS within. And this is the sum of square within some SSD in our notation, SSDW. And this is SSDB. So we have 150 observations and 3 groups, and all N1, N2, N3 are 50 in this case. So we can see this is I minus 1, and this is N minus I. And these numbers are used to standardize SSDB and SSDW. So 63 divided by 2 is 31 point something. 38 divided by 147 is about 0.26, and so on. And F value is the ratio of these two numbers. 31 over 0.265 is equal to 119. And this is F value is the same as the F value in the previous slide. And the P value, that is probability of F distribution with DF2 and 147, is more than 119.26. This probability is very small. So you can see triple star means the p-value is between 0 and 0.001. So anyway, so this has a strong indication that the different species have different sepal lengths. Yeah, so this is basically the ANOVA, how to run the one-way layout and how to do one-way ANOVA, that is the test. So in t-test, we just exactly compare 2 groups. In analysis of variance, that we compare multiple groups, and the null hypothesis is that all groups have the same mean. But sometimes we want to directly compare some group with another. If we have the tigers and the lions and tigers, lions, I don't know. So another group, maybe hyenas or something, then we want to specifically compare lions and tigers. So in such a case that we have to do t-test. And so t-test has already been done, but we have so-called the paired t-test. So the idea is ANOVA result is so vague. So so the ANOVA test is good to see if any group have any difference, but the t-test is more specific. So sometimes it's clearer, it gives clearer conclusion. And this pairwise.t.test function that implements the t-test for all pairs of groups. So basically, it's the same as t-test discussed in chapter 5, but slightly different. So I will discuss it a little more detail. And okay, so difference between these 3 species are so clear. Oh, jaguars, thank you. Yeah, difference between 3 groups are so clear. So just as a toy example, we pick up a smaller subset. So only 6 observations from Setosa and 8 observations from versicolor and 10 observations from virginica. So by doing running this code, we can restrict the data set. And the result is here. And probably there's still the Setosa and versicolor have significant difference. Setosa and virginica as well. But the difference between versicolor and virginica may not be clear because we only have very small number of observations. And we can do paired t-test, sepal lengths, then species. So format is different from t-test. So this is basically Xij. And this one, species, is a factor. And we have some option, the p adjustment none. So this is the usual t-test. We will discuss what happens when p values are adjusted. then we got these, the p-values, 0.00398. So Barsai color and Setosa are different. And the difference, the Virginica and Setosa is different as well. But the Virginica and Barsai color do not have significant difference. So next, we want to check if these results are exactly the same as t-test. And this is t-test. And actually, these are Welch's t-test. But these numbers are actually, they're slightly different. So this one, this is Setosa versus Barsai color. And this Setosa versus Barsai color, the p-value was 0.00398, but here 0.0018, so it's different. Both are significant, but slightly different. And Setosa versus Virginica, that has p-value of 0.00017. 0.00017. But here, this is 8 times 10 to the power 8. So that is 0.00008, maybe. Yep. So it's smaller, maybe just a half size of the original one. And the third one, Barsai color and Virginica, 0.262. So originally that was 0.211. So still similar numbers, but slightly larger. So these are different. Why we have discrepancy? Because estimation of sigma is different. So in pairwise t-test, basically we estimate only one sigma. So 3 groups have different sigmas, but we take the weighted average of sigmas and use this. So our assumption in the ANOVA model is the sigma is constant between groups. So if we have 3 estimates of sigmas, then we use weighted average of that. That is most reliable estimate for sigma. So the way to estimate sigmas are different. So that's why we have some difference. If you specify the option, the pool.sd is equal to f in pairwise.t.test function, then output is exactly the same as t.test. So which is correct? Actually, we don't have a general answer. So it really depends on the assumption. If you believe that the 3 animals have different variance in height or weight, then certainly, we should use just the usual t-test or pairwise t-test with the pooled standard deviation false. But if we assume that all variances are similar or the same, then it's more reasonable to use the pairwise.t.test. Yeah. So that is the explanation of pairwise.t.test function. And multiple testing problems next. So, this analysis is a little bit arbitrary because we have 3 p-values. And even though 1 p-value is not significant, still we try to claim that Setosa is different from Barsai color, or Setosa is different from Virginica. So, but this can happen if we test many pairs. So suppose that we have the 50 states in the United States. So, and we have income data for each state and see if the incomes are different between states. Maybe incomes are different. That is obvious. So maybe the height of people are different between states. Then we compare all states, the mean of ICE states and the mean of the JACE states. And we test this. Then we have 50 choose 2. So we have the 25 times 49. So maybe 1,225 pairs. So if we test all pairs, of course, some of them becomes statistically significant at 5% level. So at least probably 5% of them become significant. But that is so arbitrary, right? Because we have seen many tests. So just some of the test by chance becomes significant. So we have to need some adjustment for that. Yeah, so this is the case. If we have 7 groups, then we have 21 tests. So about 5% of these tests becomes statistically significant, even if the population means are the same. So that means the threshold for p-values should be different from 0.05. The much more strict condition is necessary. And suppose that we have the k-independent tests, maybe slightly different assumption for the all pairwise cases because the all pairs are somewhat correlated. But suppose that we have k-independent tests with significance level alpha each, and the reject null hypothesis if and only if the p-value is less than theta, then we define the theta as the number that 1 minus theta to the k's power is 1 minus alpha. For example, if alpha is 0.05 and the k is about 20, then actually the theta is about 0.05 over 20. So that is about 0.0025. Theta is about this value. Yeah, so that is the clear from the Taylor expansion of the left-hand side. So this is equal to 1 minus k theta plus some redundant, some higher order terms. So approximately the theta is equal to alpha over k. And in this case, basically the null hypothesis is rejected with probability 1 minus alpha. So that is reasonable threshold for each test, because if we have one test, the possibility that we don't reject any null hypothesis is 1 minus alpha. So if we have k tests, then if we set the threshold for each test at theta, then all tests that do not reject null hypothesis. That probability is 1 minus alpha. So basically, it's probably most reasonable to set the threshold for p-value at theta if we have k-independent tests. So because of this approximation, usually if we have k test, the threshold for p-value is the k times smaller. So alpha over k. So if we have 20 tests, the threshold for p-value should be 0.0025. So in this case, it's still hard to reject null hypothesis. And the p-value can be adjusted by this method. So this method is called Bonferroni's method. And in this case, all p-values are 3 times larger. So this is 3 times 0.211. So this was 3 times original p-value of 0.0398 and so on. 0.0398. So yeah, actually still you can claim that these two are significant. So at 5% level. So we can say that Setosa significantly has different the sepal lengths compared to Barsai color. So p-values are tripled. So it's you can just multiply by 3, but everything is included in the code. Yeah, so that is 7.1. Do you have any questions? Yeah, then maybe you can do the exercises. And I wonder what's the best way to do exercises, how many groups we should have, and so on. But we have 13. Do you have I got another question. So do we have to always multiply the p-value by the number of groups? Not number of groups, so number of tests. So in this case, 3 groups, but the more important things is we have 3 tests. So we have to divide by the number of tests. Yep. Okay, so I have the 2 exercises actually in 7.1. So maybe we can do these exercises. So the R package have the default R package have the tooth growth data and the we have, I think, the 3 kind of supplements. So no supplements and orange juice and the vitamin C, I think. So that we want to compare these groups by ANOVA. And at first you can use LM function and ANOVA function and yeah, and from the definition, you can calculate everything from scratch. And also you can do pairwise t-test. Yeah, okay, so I will make maybe 3 groups, maybe only 13 students. So we have a smaller number. And for maybe about 15 minutes. 1, 2, 3. Okay, so for 15 minutes. And I would recommend to someone to share the screen. Okay.
Professor, I think you're muted.
Sorry, the tooth growth data. If we want to change the third column as a factor, we can use this as the as.factor function. So maybe we can just name it as TG, and the third column, we want to make it as factor. So factor of tooth growth. This as a new third column, sorry. This way. Then in this case, if we check the structure of TG, then you can see those column is a factor with 3 levels, 0.5, 1, and 2. So we can fit maybe attach the TG, then you can fit the length on those level. Then we can get this maybe, for example, summary of this one or ANOVA of this one. And you can see that if degrees of freedom is 2, then we can see that those have 3 levels because this 2 is 3 minus 1. So if this is 1, probably you failed to transform this into factor vector. Okay. For other questions, I will upload the solutions sometime soon. Okay, so if you don't really have any questions, that's it for this week. So see you next Tuesday. Okay, see you.